We will start lectures in about 20 minutes. It's 11:08, so we have another 20 minutes to go. Okay? So wait some people more to come and join. Okay. All right. Now you will not interrupt me for the next hour, hour and 20 minutes, and I'm done. Then you can go. Yeah, because I want to have the clean cut connections. It's likely that I have another lecture that just follow this another class with the same lecture, and then after that I have another class with taking test.
I have all mine.
I don't think we're gonna have any problem with the philosophy, but we might have problem with it. Which is okay, because my head that I'm over there is protected by the bigger head. So it's not I'm usually supposed to do house. It's better. It's amazing for the nonsense people are talking nonsense. George Stephanopoulos was a Romanos. He says these are something happy. But his wife has a big problem.
Yeah, he got it from his wife.
Yeah.
His wife was sick for
Yeah, she says it's better. But he is asymptomatic, that's what he says. I would like to say this. From the Chinese data, we know that asymptomatic, mild, moderate, and critical. In every group, there are people having that. So, nothing is sure. Okay? It might start really, really nicely, and then all of a sudden you can do real bad. But one thing I was reading is that interleukin, very important thing in the human body, interleukin 6. If that thing goes over a certain measure, that is a predictor, very strong predictor for what the case is going to be. That's good. So groundbreaking research for all the because for instance, Chinese government told me so they really warn about it. So now the others have gotten they're all in conforming to this Chinese government. So that's a predictor of the critical case. So now they're thinking maybe there's a way to change this. Because it seems to if you get killed by your own body, your own body flaws your mind dramatically between the others. And that actually kills you. So this is they can somehow manage to cut this down. It's more that interleukin 6 gets higher if you exercise. Very interesting. So that might be the reason why men might have it more, make them might have more natural. And obviously children might not have it. Interleukin 6. This is actually very important in our body. It's related to many diseases in a positive way. But this time might be so positive. Belgium with a more than 10% mortality case went people is Spain. France also 100%. So whoever says the death rate is low, look at the scans, they're lying. It's not at all. We don't even know what it is, but it's not going to be. It's definitely going to be 400%. Thailand has 5 new cases, Croatia 50, and 2 deaths. Russia has 2,500 something new cases. But they are doing a tremendous amount of testing. They actually doing as much testing in general, not only 3 million tests. Russia, they are really doing a huge effort on tracking the testing, but it's just run out of control. So they are doing a lot of testing. On the other hand, here in Indonesia, 270 million people, almost double than Russia. And they have conducted less tests than Slovenia, which was 2 million people. So they have hundreds of dying, and they can't even say that they died from it, which is very big. Russians are doing tremendous effort. Russians are doing tremendous effort.
Nobody wants to touch.
Russians are doing tremendous effort. They can't stop it. So they should have done that earlier instead of fighting. China was confused that they were not 100 cases. They get it in the promise that is involved in Russia. Far as Russia. They have Russians that were more than 100 cases. Chinese in the hard is the there they have developed the lockdown promise and they force they close the borders. And Sweden are trying Russia route and fill it up. They can make 2 million euros. Austria's doing what? Austria's opening some shops. Austria has much better control because when they started mandating masking on, it was a March 25th and 27th, they immediately dropped the number of cases, which is interesting. Czech is the same. Yeah. When you record this automatically record that, but then I have a hard time to record. But I will down because once I download, I actually have we can see. It stays on YouTube, but on my states. I can use this before. Because I'm expecting folks more than a radio situation. I think there's something much of normal. It's all gonna, not everybody is gonna be famous. And the situation is very yes. Not in question, but football. So I can't say. But 2 servers will die. So here, and 2 of them hospital. So younger people in that way. So what's it look like in that? If you don't make the Vermont, they don't try to, but they like it. You can stay with that. That's cheap.
It's not, it's just not black and
Yeah.
it is not fun.
Yeah.
It's good,
But they will, when they change the government, they will restate it exactly on that sheet. Still about 5 minutes to go before we can start and get some more people to join. Okay, folks, we're going to start the lecture today. We have the lecture on polynomials. The word polynomials comes out to Greek word, actually two Greek words, poly and nomos. And polynomos would mean like a multi-order of some sort. And this is, of course, going to be about numbers. The you heard the word nomos probably before, and it's in the part of the word economy, economos, part of the word of astronomy, astronomos. So this is nothing new. So we're gonna have the a little explanation what a polynomial is. Okay. Now the idea of polynomial would be that it would represent a number. So what kind of number? Well, a variable number, something that is going to have a variable content. So for example, something like this. Okay, you have one variable here. That variable is the x. And now depending what an x is, that would be a different number. This is what we call a polynomial. Now, this is not anything very new to you. We actually have polynomials. Whenever we write any numbers, we actually have polynomials. We have, for example, 237. That will be 2 with a 2 multiplied with the 10 square. Put here 10, and you have a 2 hundredths. Put here 10. You have a 3 times 10 or 30. And then, of course, you have a 7. I should have, for example, minus 7, but I have plus 7. So maybe I could just put it this way, so now you have it. Okay, so whenever you write a number in a Hindu-Arabic notation, you read that number is 237. It's ordered in a particular way. So in the first place here, or should I say the last place, the first unit is 1, then you have a 10, then you have 100, and so on. So this is similar the way you write a polynomial. Only, of course, you don't have a 10 here. You can have something variable. You can have any number you like. Okay. Now, in Hindu-Arabic notation, we use 10 for a base. So we have unit, 10, 100, and 1,000, and so on, because I guess we have 10 fingers. So that's what we use. If we are living in some kind of other place in the universe, there might be people that have some aliens that have, I don't know, 6 fingers, then they will probably use the base 6. And maybe you have some similar notation. Okay, now what's the key about polynomial? Number one, the powers can only be non-negative. So you can have variables, but you can't have variables with negative powers. So for example, x with a -1 could not be a polynomial. You could not have that as a polynomial because the power is negative. So the power could only be either positive, like 2 and 1 here, or 0. That could be a power. All right. You could have multiple variables. So, for example, that's another polynomial. It has 2 variables, an x and y. You can have more than that. We're usually not going to deal with the more than one variable, but you could have that. So polynomial could have more than one variable. We have some special names for polynomials. So for example, both of these would be called trinomials or trinomials because they have 3 terms: 1, 2, 3. 1, 2, 3. So those are trinomials. This is a binomial. Bi has 2 terms: 1, 2. And then, of course, you could have a single term like that. Now, this is called monomial. Monomial. So you have trinomial, monomial. You can have binomial. Check the lecture. You can have 4 terms. That would be, I guess, quaternomial, but we don't have that kind of name. We don't use it. And then 5 terms will be pentanomial, and so on. You get
just use those Latin names for for numbers that you need to count the terms, right? So you have 7 terms, you would probably call it septanomial. But we're going to call it just polynomial. So in particular, we're going to have, when we have 3 terms, we're going to call it trinomial. That's going to be important to us down the road. Binomial is something that has the 2 terms, and monomial is something that has the 1 term. They are somewhat more important than the others, but there are also many other polynomials. Okay, more. When the polynomial is written in this format, like that, then we call it's written in the standard format. Standard format means that the variable content on the count of the variable as the factors is the biggest forward, and then as you go toward the right, you have less variable factors. So for example, you have x times x here. Those are two variable factors. You have x here, that's 1 variable factor. And then you have 0 variables here, so that's 0 variable factor. So when you write polynomial like that, we call it, it's in the standard form. Okay? More. So the polynomial in a standard form cannot have anything like this. Right? You could call this, you could say, oh, I have a quadrinomial here, I have a 4-term polynomial. No, you don't. You have this polynomial is not written in a standard form. So if it's not written in a standard form, we're not going to call it whatever we would call it. I don't know, quadrinomial or something. Because these two can be simplified. You have a 2x squared minus x squared, which makes it 1x squared. So instead of having this, you should have this. So now it's a trinomial. So it has to be, the polynomial could not have 2 the like terms. If you have 2 the like terms, you need to add them or subtract them, whatever that is to be done, but you cannot have 2 or 3 the like terms. You can only have 1 term that has the same factors, variable factors, but not more than 1 term. Okay, so that's an important thing to remember. Another thing, these guys here are called coefficients. Okay, coefficients are the numbers that are the constant number that are factors in a term. So here you have 2 times x, so 2 is the coefficient of this term. Here you have a 3 times x, 3 is the coefficient of this term. And here you have 7. And that's the only concrete numbers. So you can just say this is simply a coefficient, a constant number. So that what we call them coefficients. You got to remember that because we're going to use that all the time. The one forward in a standard form, the one which is a factor with the biggest number of variable factors, is called leading coefficient. So this is a leading coefficient, this one. And this is also called a leading term. Okay, this is very important because there are certain characteristics of the polynomials that polynomials keeps because of the leading term being in a particular way. And that's important for algebra. So you need to know what the leading term is. You need to know what the leading coefficient is. And you also need to know what is the number of variable factors in the leading term. The number of variable factor here is 2. How many variable factors you have? You have x times x. So you have 2 variable factors. And this 2 is called a degree of polynomial. So to be able to identify degree of polynomial, you need to find out what is the leading term. Then you need to count the number of factors in that leading term that are variables. So you have, again, x times x here. That count is the degree of the polynomial. Okay? There is more rules about it. the coefficient does not have to be an integer. Now I wrote 1, 2, 3, 4, 5, but that doesn't have to be. It could be any number. So for example, 2.1 is perfectly fine. It could also be a fraction. 5.14 is a fraction, but I could just write it as a fraction like this. Okay? So coefficient could be any number, any real number. Okay? And you don't have to have the term in a decreasing order so that you have to have every single degree in a term. For example, you would expect to have an x squared here, right? You have an x cubed, and then you have an x, and then you have x with the power of 0. You can write like that, but we don't usually write like that. X with the power of 0, we just don't write. That's 1, right? So basically, you could say, well, where's that x squared? Well, if you want it, you can have it. So you have a 2.1 x cubed plus 0 x squares. You don't have any. Minus 1 x plus minus 1/2. Okay? This is not a quaternomial. It's still a trinomial because this term is really a 0. So we only count a significant number of terms, not the ones that are zeros. Right? Okay? By the same token, okay, the leading term must be non-zero. That means the leading coefficient must be non-zero. Okay? So you cannot have here 0. If that is the case, then you don't have a leading coefficient, and you don't have a leading term. You can still have a polynomial. This is a polynomial. Doesn't have leading terms because it doesn't have non-zero terms. Everything is 0. This is just a 0. This is a good old number, 0. This is also a polynomial, a special one. We don't have any polynomial any other polynomial that looks like that. No leading term, no leading coefficient. Everything is 0. Yet we will still allow this to be a polynomial, so we call it polynomial. Okay. This is a polynomial, and the leading term is 2.1 x cubed. The leading coefficient is 2.1. So it does have a leading term, non-zero term, does have a leading coefficient. That must be non-zero. Okay? This one does not have it. Okay? Also, this polynomial has degree 3 because the count of the variable factors in the leading term here is 3. X times x times x. Those are 3 variable factors. This one does not have a leading term, therefore it does not have a degree. This is a polynomial without a leading term, without leading coefficient, and without degree. Okay? Let's try something else. Is this a polynomial? Yes. Okay. Now, this is a monomial because it has only one term. Does it have to have a variable? No, it doesn't. It's not required to have a variable. This one doesn't have any variable. It's just 3. Good old number 3. Any number you like. It's now a polynomial. It does have a leading term. This is the only term, and it's not 0, so it's a leading term. It does have a leading coefficient. Yes. 3. That's a leading coefficient. How about the degree? Well, degree is the count of the variable factors in this leading term. How many variable factors you see? 0. So the degree of this guy is 0. So this is a perfectly good polynomial, monomial, single term, 1 leading coefficient, 3, which is the same as the term, 3, which is the same as a polynomial, 3, with a degree 0, because you have that many variable factors in the leading term. So you got to remember that. Those are important notions. You might think about, oh, this is just language and jargon, right? In mathematics. No, it isn't. Actually, these are very important notions because down the road we will actually see certain properties of polynomial based on what those things are. So if you don't know what those things are, you're going to have a problem, right? Like some of you have a problem when I mention integer. You don't know what that is because you didn't pay attention. Or when I say absolute value, you don't know what that is because you didn't pay attention. So this time, the same thing. You will need to know when the polynomial is in the standard format, when the polynomial has a leading term, what is the leading coefficient, what is the degree of the polynomial, and how many terms it has. Okay, so those are important things. Okay, so what do we do with polynomials? Well, that's a good question. Well, since polynomials are numbers, a representation of numbers, we do lots of different things. Well, we do certain things we don't do with the concrete numbers. So, which is identifying what is the degree of the polynomial. Let me write one example. So, there you go. That's an example I'm picking up from the lecture. Okay, so if I'm asking now, what is this? You can say this is a trinomial. It has 3 terms. And it is a polynomial because all the powers of the variables are non-negative. We don't have any negative power. So it is a polynomial, perfectly fine. Is it in the standard format? No, it isn't, because this guy has more variable factors, and it should be in front of this guy, which is only one variable factor. So we can put it this way. Now we can write the rest. Now it is in the standard format. Now it will be also in the standard format if I replace these two, because they're both with the same number of variable factors. Now you can say, what is this is the same thing, by the way, because we know that commutativity works. So this minus this is the same as negative this here, and then this one here, because we can switch 2 numbers in the real number story. These are all supposed to be real numbers anyway. Okay, so I can say here, so this is in the standard format. What is the leading term? The leading term is this guy here. What's the leading coefficient? The leading coefficient is -1, because that's the number multiplied with the x cubed y squared. So that's a leading coefficient. I can say also now what is the degree of this polynomial? It is 5. So leading coefficient is -1, degree is 5, because I have 1, 2, 3, 4, 5 variable factors. So 3 x's, x times x times x, and then y times y. Okay, so this is one of the things you can do with polynomials. It's just a play. You can find out what is the degree, what is the leading coefficient, what is the leading term. You can reorder them in a fashion that you can give a standard format, which means the degree of the terms. So the term also has a degree, which is how many variable factors you have in the term. So the degree ought to be dropping as you go toward the right. Okay, what else can you do with polynomials? Well, you can evaluate them. For example, you have 3x squared minus 2x plus 5. Let's call this polynomial Peter. We would write like this, meaning Peter is in the terms of x. What does that mean? It means that this polynomial, that I just call it P, has one variable. Variable is x. Okay? So this is a variable number. You don't know what that is because you don't know what an x is. But if I give you an x, you can evaluate it. So if I tell you the x is equal to 3, then you can evaluate Peter in terms of 5. Now 5 is now in place of x, is equal to 3 times 5 squared. I'm replacing x with a container, putting 5 in it. 2 times 5 subtracted, because that's now in place of x, 5. And again, I'm using container, and now I have another 5 here. And so this turns out to be, I don't know, this is 75 minus 10, which is 65, plus 5 would be 70. So I have the evaluation of polynomial. To evaluate polynomial, if the polynomial is not a concrete number, in which case it's the same as its evaluation, somebody need to tell you what the value of the variables are. Now, when you have the values of the variables, you can evaluate the polynomial. So if the polynomial has two variables, then you need to know both. For example, let's say I'm going to call it Steve. Steve is in terms of x and y. And now it looks like this way. X squared y minus y plus 3. It's a perfectly good polynomial, perfectly good looking polynomial. It's a 1, 2, 3 terms. Okay? If somebody says evaluate this polynomial, that person needs to tell you what is an x and what is y. Because without that, you cannot evaluate. So you need to find out those values first. So if I tell you that x is equal 1, and if I tell you that y is equal minus 2, then you can start evaluating. So what you have here is you're going to put the 1 in place of x, you're going to put negative 2 in place of y, negative 2 in place of y, and then you will evaluate. So this is good old routine we have. Anytime we have algebraic expression, polynomial is algebraic expression. So you're replacing the variable with the value of the variable. But you use containers, because if you use containers, you're not going to make sign mistakes. So now you have here 1 multiplied with negative 2, which is negative 2. And you have positive 2 here, negative 2, and then you have 3. So I'm getting 3 as the end. And that would be the evaluation of Steve at 1, negative 2. 1 for x, negative 2 for y. So this what I wrote here, I hope you're not confused. This is just the what a polynomial is, and I'm having here a label for this polynomial. I'm calling it Steve is in terms of x and y. So x, comma, y. I'm telling you there are two variables in this polynomial, and that's an x and y. And this is exactly what Steve is. Okay? So these are the things you do with polynomials. You evaluate them. I suggest you read the lecture because you're going to evaluate a lot more in the lecture, which is a good practice for you. Okay? Now, what else you do with polynomials? Well, I already said polynomials are numbers. So you do everything you do with numbers. And that would mean, what do we do with numbers? Well, we add them, subtract them, multiply them, divide them. What else? I guess factorize them. And we have certain rules about numbers that numbers obey, which is going to be the same thing with polynomials. We do long divisions with numbers, long multiplication, all sorts of stuff. Well, exactly that we're going to be doing with polynomials as well. Okay, so you might think about it. All right, so this is something that is not much of a surprise, and it isn't. It's something you've seen before. The addition will be done really in a very straightforward manner. So I'm going to write down one example. So I have something like this, a polynomial, and I want to add to this polynomial, I want to add another polynomial. Something like this. Okay, so what are you going to be doing? Right, first of all, you know that these are numbers. So 1, 2, 3. 1, 2, 3, 4. This is also a number, and this is also a number. And you know from the story about real numbers that you can shuffle the stuff. The numbers can be shuffled around, right? You're using basically commutativity and associativity to be able to shuffle the stuff around. So you can do that here, okay? And you also need to identify why would you want to shuffle that. And you need to identify what are the like terms, because the like terms are the ones that you can add. So you look at this one here and this one here. They're both about squares of x. So they are the like terms. The like terms are the terms that have exactly the same variable content. So what you have here is xx. What you have here is xx. They have exactly the same variable content. So you can add the like terms, the ones that have exactly the same variable content. Why? Because you can use the distributivity. That's a property that you use to add terms like that. Then you have here x's, and you have here also x's. So you can add these two. Then you have numbers. Or should I say constant term? Constant term. The term that has only number in it. Okay? And then you have this guy, this lonely guy, doesn't have any cube anywhere else. And you already know this is going to be the leading term anyway, because it's the x cube, and that means 3 variable factors, x times x times x. And no other term has that many. So you can put it forward immediately. So you're going to have negative x cubed. It's going to go forward, leading term. Then you're going to add 2 x's. X squares. So you have x squared here and x squared. When you add that, you're going to have 2 x squares. So you're really realigning and then adding the like terms. Then you're going to have here negative 2x's and negative 2x's, which is going to be negative 4x's. Okay? Now, I wrote this stuff in the lecture a little longer because I was first realigning them, then I was adding that. So, but here I'm doing that immediately. And then you have a negative 3 and negative 1, and that's negative 4 total. And you're done. That's how you're going to add polynomials. Nothing special. Very easy stuff. You can also do that in a vertical format, which is not much of an advantage. Okay? It's a very big advantage when you're doing that with the when you have vertical format, when you're adding or subtracting Hindu-Arabic numbers, because there is a conversion and alignment is very nice. So, for example, when you add 273 and 1255, what you really do is you align the floating point, and then you add unit and unit. You get an 8. You add 10 and 10. You got 12 of them. So you write 2 and 1, 12, right? 10 times 10 is 100. So it's a conversion. So you have hundreds and hundreds here, and one that you just, we call it carry on. So you got the 500s, and then you have 1 here. So it's very nice because it's nicely positioned. The alignment is straight at the floating point. But you don't have that with polynomial. Polynomial don't have floating points. So alignment is a little bit more problematic. You have to be very careful. So these two are actually easy to align. So you had x squared minus 2x minus 3. And then the other one is negative x cubed plus x squared minus 2x minus 1. So when you add these two, you can do that. I mean, it's negative 4, negative 4x, 2x squared plus and negative x cubed. So that's a vertical format for addition. If you want to use it, fine. You will see in your homework you will be asked to do the vertical format, but nobody will be checking it, so you can do it any way you want it. You just need to have a result, right? I'm not going to emphasize this. I'm not really interested in vertical formats of additional polynomials because, again, the alignment is not natural. There is a slight problem. I'll show you that in another example. So, for example, I have to subtract 2 polynomials. So one of the polynomials that I want to subtract, this is an example from the lecture, is x cubed plus 3x squared plus xy plus y. And that's my minuend, and now I have to subtract the subtrahend. This is how the numbers in addition are called, and subtraction are called, right? The one you are subtracting from is minuend, the one you are subtracting is called subtrahend. So I'm subtracting now, the second one is 3x cubed. And then I have negative 1.45 xy. And the last piece of that term is negative 2y. Okay? Now here's a little example why you have a problem here. First of all, if I do it horizontally, I wouldn't have a problem. Because I can see here, I have a cube, and I have a cube. And I know I need to subtract them, which means I need to change the sign here, everywhere. negative, positive, positive. You got to remember that. You can just write the whole new thing to change the sign to avoid any problems you're going to have down the road. So it's going to be negative 3x cubed, positive, negative, negative, positive 1.5xy, and then negative, negative, positive 2y. Okay? Now you can start adding. It doesn't even matter which part is which polynomial. All you have to think of is, here you have a cube, here you have a cube of an x. So when you want to add these two guys, you're actually going to be subtracting, right? X cubed minus 3x cubed, you have a negative 2x cubed. Done with these two guys. Then you have an x squared. Well, you don't have any x squared for it down the road, so you can just simply copy this one. Then you have an xy. You have one here, you have another one here. Some people cross the stuff. I don't like to cross the stuff because then it looks like cancellation. We're not canceling, we're adding. So I have xy and 1.5 xy. So it's going to be 2.5 of them. Right? You're basically adding the coefficients. And finally have the y in two places. You have 1 and 2 down there. So you have a total of 3. So if you do this kind of accounting, it's much easier. All right? It's relatively easy to do that. It's not a big problem. I don't see why would I want to do any vertical subtraction here. But if you want to do vertical subtraction, this is how it's going to go. You're going to write the minion on the top. And then you're going to write underneath something that you want to subtract. But you're going to have to change the signs because you really don't want to be subtracting. You want to be adding. So you're going to have negative 3x cubed. The x cubed under x cubed. Then you're going to have positive 1.5xy. There's your alignment. The unit under unit. So you have to have the variable under the term with the like content. They have to have exactly the same variable content. Those are the like terms. You can only add the like terms. See, there's a hole here. That doesn't happen when you're dealing with numbers because when we have a hole, we just put 0 there. So for example, you have 2037, you're not going to write this way, this is 237. You just put 0 here. So you have no problem with alignment. You will still align with the floating point. But here, we don't write 0. So you have to move this one here. You don't write it here because you're going to make a mistake. You're going to be adding wrong terms. And then you write here negative 2y. So just this process of alignment is already enough and tedious that it makes me not want to do that. Okay? And now you can start adding. So you have negative 2x cubed. You have 3x squared. You have plus 2.5xy. And you have negative y, which you had the same before. Right? So instead of doing this vertical format, I can just do it horizontally. So I am not going to force you to do anything on vertical format. The homework says do it in vertical format. If you know how to do it horizontally, do it horizontally. The only thing you need to do in the homework is to write the correct answer. Okay? And so the advantage of vertical format that we have in the Hindu-Arabic notation when we are dealing with those numbers written like, 2357 and stuff like that, is that we can align them at a floating point. We always do that, even with decimal numbers. But here you don't have a floating point, so you cannot align floating point. Right? Well, actually, you do have a floating point here, but this is not really a floating point of the polynomial. It's just a floating point of 1.5. Right? So you have to be careful. Okay. So what else we do with polynomials? Well, we'll multiply them too. Now, multiplying polynomials is a whole story about it, and we're going to be, doing the piece by piece. First of all, you can multiply monomials. Monomials are one-term polynomial. So you have one-term polynomial times one-term polynomial. So how is that going to look like? Well, it's very simple business. So I have something like this. You want to multiply these two guys? You're just simply going to use power rules. First of all, you're going to shuffle. And you can shuffle because, of course, you're dealing with the real numbers. So even if it's written in a way the polynomials are written with this little story about the variables, right? You might have some variables in it. So you can think of it, okay, a variable, I don't know what that is. Well, they are real numbers. So that's all you have to remember. Everything you see here are numbers. This is a number, 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 and this is a number. And this is also a number. So there's nothing special here. So you can follow the rules that you know about numbers. For one thing, you can shuffle this. So what does a shuffle mean? 2 times 3 times x squared. So you're going to be multiplying numbers times numbers and powers to powers. So you multiply 2 and 3, you're going to get 6. Now, you're allowed to do that because shuffle works for multiplication. That's, again, associativity and commutativity, which is applied repeatedly, but you can just simply remember, you can always shuffle factors. You can shuffle factors and terms. You can either shuffle terms or you can shuffle factors, but not both, right? So here you have factors only. So you shuffle factors. 2 times 3, which is 6. And now you're going to use a power rule. X times x squared, of course, it's an x cubed. And you're done. So again, shuffle, power rules. That's very easy to remember. I'll give you another one. You don't even have to shuffle if you know what's going to happen. Basically, you anticipate what's going to happen, so you don't have to shuffle. You can remember. So I have 2y cubed times -5y squared. All right? How's that going to be? Number times number. I have -2 and -5, and you multiply that, you get 10. So I'm not going to shuffle. I'm just simply going to remember. I'm multiplying coefficient and a coefficient. Coefficient here is -2. Coefficient here is -5. That's the constant factor. So I get 10 when I multiply them. When I'm multiplying y cubed and y squared, I'm using a power rule. Which power rule says you just have to add the powers. 3 plus 2. Okay? Now, if that is not clear to you, do that step by step. But that's the story. Very simple business. Okay? Even if you have a multiple variable, you're going to use that. So let me do something with the multiple variables. I'm still talking about monomials, which means one term times one term. Okay? So let me do another one that is in the lecture, -0.5. And I have x with the power of 5, y. Okay? And the other one I want to multiply with is -7, x to the power of 4, y squared. And for the purpose of aesthetics, I'm going to put this one in parentheses too, just so you can see that. It was not needed, but I can put it in. Okay? So, what are you going to do here? You're going to multiply coefficient times the coefficient. Then, you're going to use power rules. So what are the coefficients? -0.5, -7. The result is going to be positive. 7 times 0.5, this is 7/2, it's 3.5. Done. The coefficient multiplication is done. Now, you're going to multiply the powers with the same base. You want to use a power rule. You can shuffle this stuff, but you don't need to. You can just remember it. You can multiply powers with the same base. So x's with x's. So you have x with the power of 5, x with the power of 4. That is an x with the power of 9. I'm using a power rule. 4 plus 5. If you just want to count, it's going to be x, 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 x. How many? 9. And then y. You have here 1, and you have here 2, so that's total of 3. And you're done. So again, This is multiplying monomial time monomial. You have to remember you multiply coefficient time coefficient, and then you multiply power time power. But of course, power has to be with the same base, because if you can't, you can just, for example, if I have here z, then I would be able to multiply x and x. But what will happen further on? I have y, and I have z squared. I can't multiply these two, so I'm just going to writing them. Down I have the result. Nothing special. I can't apply the power rule by multiplying y times x z squared, y times z squared. I can just simply write it down because there's nothing else to do here. So again, when you use a power rule, you have to use a specific power rule. There are 6 of them, so in this game is one of them we are using. So you have to make sure you're using the correct power rule. Okay, now, what else can you have? Well, polynomial doesn't have to be monomial. It could be 2-time, 3-time polynomial. So what do you do then? Here's an example. So I'm multiplying 1-term polynomial, or as we call it, monomial, and 2-term polynomial, as we call it, binomial. So you might wonder, well, how do I do that? Well, it's nothing special. Again, you have a number here, you have another number here, and you have another number here. So when you think like that, then you can see distributivity in action. Distributive property. You're going to have to identify the terms. Term, term. Always remember the sign for sign belongs to the term that follows. So you have to multiply this term and this term and this term and this term. That's called distributivity. Nothing special, nothing new here. Okay? So when you do that, you can write it down if you're not quite sure what's going to happen. X squared times 2x. That's the first thing you need to do. Plus x squared times -5. Okay? That's the story. So now you can finish the job. In here, you have a 2x cubed. And in here, nothing special, -5x squared. We like to write coefficient before we write the variable part of the term. That is part of the standard format. So you don't write x5. That's kind of confusing. In some notation, that could be the 5th x, right? Something like this. So we don't write like that because that could be confusing. So we write, instead of that, we write 5x. So that's a part of the standard format. I forgot to say that before, but that's the idea of a standard format. So again, distributivity in action. You can do that with the multiple terms. Here's another example. I'm multiplying 3x squared with x squared minus 3x plus 5. All right? Again, count the terms. 1, 2, 3. The plus or minus sign belongs to the term that follows, and everything is just addition. So you have here x squared plus -3x plus 5. So you read everything as an addition rather than a subtraction. Right? Subtraction is for elementary school students. We see everything as addition. Okay, so what do? You multiply this one with this one, you multiply this one with this one, and you multiply this one with this one. That's the strategy. What is this strategy about? Well, that's a distributivity. Apply twice, though. So you have to multiply this time this one, and then this one times this one. That's the first time, and then when you multiply this one times this one, then you actually multiply this one times this one, and this one times this one. So you're using distributivity really twice. But you can just do it at once. Okay? These guys, every one of them, 3 terms, going to be multiplied with this guy. That's it. And if you're not quite sure what's going to happen, I want to write it down. 3x squared multiplied with x squared plus 3x squared multiplied with negative 3x. So this is number 1, number 2, number 3. I'm just done with number 2. Number 3, 3x squared multiply with 5. Okay? Most of people won't write like that. They just simply write whatever the result is. I'm just saying that's okay if your brain works fine. But if you start making mistakes and forgetting the signs, then you know, like the good old story goes, it's not a stupid mistake, it's a stupid person who is making it. Right? So write it down, and once you're sure that you know exactly what you need to do, then do it. So here it's easy piece. You have 3x to the power of 4. Here you have 3 times negative 3, which is negative 9. You have x squared times x, which is x with the power of cube. So if you can count, it's easy. If you can count, it's easy. 3 times 5 is 15. And you just have an x squared. And you're done. You don't need to rearrange anything. Sometimes you don't need to rearrange the stuff because it might not be in the standard format, but here it is. This is a polynomial of degree 4, leading term, leading coefficient, already forward. This one is the next one. Go. So in the second place, this one is the smallest number of variable factors, 2 x's, last place. Everything is done fine. And there's no any double like terms. Every one of them is a different one in terms of a likeness. Okay? Now, the next story goes, which is called how do you multiply binomial with binomial, which is called FOIL method. Okay? Now I'll explain to you FOIL method on example first, and then I'll give you the reason why we do that. This is straight out of the lecture. So this is binomial. So I'm multiplying binomial with binomial. Two-term polynomial with two-term polynomial. Okay? This is like you're pairing people. So you have 1, 2, 3, 4 people, and here you have 1, 2, 3 people. How do you pair these people? You need to pair everybody with everybody. This is like you having some tournament, and there's a group here that needs to play with this group here, and everybody needs to play with everybody this way. 1 pair, 2 pair, 3 pair, 4 pair. Everybody's paired with this guy. Now, 1 pair, 2 pair, 3 pairs, 4 pair, 8 pairs so far. Everybody here is paired up with this guy, and I have to do the last thing here. These guys, these guys, these guys, and these guys. And I have 12 pairs, which you should expect, 4 times 3, 12 pairs. Okay? If you can remember the strategy, it's easy. So everybody here has to be paired up with everybody here. So you're going to have this times this. There's a term here. There's a term here. Then you're going to have to multiply this times this. Then you're going to have to multiply this times this. And you're going to have to multiply this times this. This strategy is called FOIL. Okay? What I have here, you need to multiply x times x, which is first times first. Then you need to multiply this times this. Which people call alter times alter. Then you're going to multiply this times this. That will be inner times inner. And finally, you have to multiply this times this, which is last times last. Now you see the word FOIL, where it's coming from. I'm quite sure you have seen this in elementary or high school. Do you need to have this order? No, you don't. You can have philo or olive or loiful or lifeful. I don't know. Makes no difference. The only thing that needs to be done is that everybody here needs to be paired up with everybody here, and that's how you get them multiplied. So, but the word FOIL is kind of easy to remember, so you can do that. X times x is an x squared. X times 2 is 2x. Negative 3 times x is negative 3x. And negative 3 times 2 is negative 6. You're not done. You still have to write it in the standard format. This is not in the standard format. You do have an x squared forward, which is good, but these two guys are alike, so you have to simplify. Negative x, 2 minus 3. And the last one is negative 6. You're done. So I multiply 2 times 2, which is with 4 terms, 4 products, but at the end you end up with 3 terms. It might be even 2 at the end, depends. Okay, so you have to be careful. So again, you might want to ask question, where's this coming from? Right? Intelligent people always ask question, why? How? Well, distributivity. It's in the game. So when you're distributing, when you're using distributivity, you can consider this to be one number multiplied with 2 numbers here, which means that this number had to be multiplied with x, and then this number had to be multiplied with 2. That's the first distributivity. Then you have a second distributivity. This x times x, negative 3x. Then you have a third distributivity. X times 2, negative 3 times 2. And there's your FOIL. First times first, outer times outer. Oh, it's right here. Ooh. Inner times inner here, and last times last here. Oh, so I don't have FOIL, I have file. Makes no difference really. Right? Because you can switch these two, and I have the same number. So that's where it's coming from. It's a triple distributivity. Once here, 2 times more here. So when you're dealing with the FOIL, all you have to remember, that rule is fully justified by distributivity on steroids. 3 times distributivity, you have FOIL. So you can always use FOIL because it's justified by the property of distributivity. Okay? So ordinarily, you're going to write that in the same row, but if you're not quite sure, you might want to use the containers, which I did, or you might write it in multiple rows. So say I have something like this, x squared, x cubed minus 4 gets multiplied with the 3x minus 2. Okay? So some people do it like this. Oh, I don't want to make a mistake. I'm afraid I'm going to make a mistake. Okay. So FOIL, F, first time first. Outer time outer. -1. So you should actually put everybody in a container. Container preventing sign errors. That's important. Then what am I missing now here? Okay, inner time inner. And last time last. Okay, I made too much writing here, really. So I have to spend a whole board just to do that. So you can just do it in a single line. So this is 3x to the power of 4. This is -2 x to the power of cube. This one is -12x. And this one is +8. And you can say you're done. because this is in the standard format. Perfect. I don't have to do any simplification because I have 4, 3, 1, no variable factors. They're all dislike terms. They're not equal. I shouldn't say equal. They're not alike. So you can actually keep it this way. And it's already the one with the biggest number of factors here, and then the next one, and the next one, and the next one. So it's perfect. It's already in the standard format. Okay? So this is the foil in too much writing, right? You can just simply write in a single line. It's up to you. You have to learn this rule, because if you don't, you're going to make mistakes. And another thing also, containers are important. Anytime you don't write containers, if you dislike writing containers, you are probably a prime example of a person who's going to make sign errors, right? So if you see yourself in the previous tests, wherever you were taking the test, and you were making sign errors in those tests, that's the reason why you should start really using containers, because you probably don't use containers, and you dislike using containers, and that is conducive to making sign errors. So you have to start using containers. Okay, so binomials in general, when you multiply binomials with trinomials, so not just 2 by 2, which is the FOIL, because you have a 2 by 2, so you get the first time first, outer time outer, inner time inner, and last and last. But if you have 3 things, then you have a middle guy. So how is that going to work? So I'm going to give you an example. And I'm going to ask you to read in the lecture. In the lecture, you have more, I don't know. No, I'm trying to copy that from the lecture, but I don't have to. I can just put up something on my own here. But let's say I have here something like this. Okay, so you're multiplying 1, 2, 3, 1, 2, trinomial with binomial. Okay, trinomial or a trinomial, I don't know how you call it. Trinomial is the same. Binomial. Okay, again, the pairing is the game. You got to remember the pairing game. So you have pair this 3 with these 2. How? This, and now I'm lost. Right? So you need to have some strategy. Okay, I'll give you the simple strategy. This one time paired with this one paired with this one paired with this one. So everybody here paired with this guy. That's a simple strategy. And then everybody here paired with this guy. Very simple. You're going to have everybody with everybody. That's the simplest strategy you can use. If you can find another one that works for you, fine. But this is the one that really works nice. Okay? So if you can remember that, it's not a big deal. So we want to count the terms. 1, 2, 3. 1, 2. Remember, sign belongs to terms that follows. You got to remember that. It's an important concept. So now you have everybody here, 3 of them, paired with this guy. That's a strategy. Once you finish that, everybody here pair with this guy. But you are not just pairing, you're multiplying. So you're going to write A times A squared. This times this. Then this guy times A squared. Then this guy times A squared. Do I need parentheses for 2? No, I don't. But now I'm just writing it as a good habit. Now I have everybody here paired up with this guy. Now I have to do exactly the same thing to pair them up with this guy. So I have A, I have negative 2B, and I have 2. and they have to be multiplied with -1. Uh-oh. And then multiply time -1 plus time -1 time -1. This guy multiply with this guy. This guy multiply with this guy. This guy multiply with this guy. I think this is easy to remember, right? I hope it is. It's really not that much of a trouble, I think. But you have to finish it. So I have here power rule, a cubed. Here, -2a squared b. Oh yeah, you can write ba squared, but kind of nice to have in alphabetic order. And then 2a squared. That one over there. Here, -a. Here, positive 2b. And the last, -2. It's a good idea to count. So you have everything at, you didn't lose anything. So you have a 6 here. 1, 2, 3, 4, 5, 6. Good. Now the next thing would be to get it in the standard format. Well, it already is. Leading term, leading term. Oh, this is a holy moly. This is a polynomial with two variables that have two leading terms. Yes. Because this one has a 3 variable factor, this one has a 3 variable factor. Which one goes first? Either. Okay. Yeah. You can have two leading terms if you have multiple factors. You might have an x cube and you might have a y cube. Both of them are with 3 factors. Which one goes first? Your choice. The same thing here. This one, this one, this one, this one, all of them dropping in terms of number of variable factors. They're all perfect in order, nothing special to nothing to adjust. They're all unlike, so I'm not going to be able to add them. Good enough. Okay. Can you do vertical multiplication? Yeah, you can do vertical multiplication here. So this is, I'm going to show you just an example of vertical multiplication, which is just waste of time. But I know you're going to be asked that in the homework, and you might be puzzled, what the heck is a vertical multiplication? Well, nothing special, really. It's done like with numbers. So you would write something like this. I think I have -1. I already forgot, yeah. And then you have that good old story when you have a vertical multiplication, how that goes. This time this, this time this, this time this, and then the next line. And now it's an alignment problem. This time this, and you have an a squared, so you have to find another place for it. A squared, two of them, because I just multiply with this guy. Then this time this, -2 a squared b. I'm running out of space already, which is plus. I can't change the sign here. And then I have another one. This time this, which is a cubed. And now you have to add that. This is nasty. It's not attractive because we don't have this typical alignment that we have with the long multiplication where we're dealing with a Hindu Arabic notation like those 356 times 27. Because alignment that is always really nice. They're the floating points, nothing to worry about. Where's the floating point here? Nowhere. So you have to find a place for them. You can't put them under here because these are all different guys here. So they're unlike. So you have to find some other place for it. And then you have to add. And so what do you have? A cubed minus 2a squared b plus 2a squared. And then you have this, -a plus 2b, -2. It just looks more confusing. No game. You still have to do every multiplication you have to do before, but instead of just simply writing in a single line as it goes, you're going to start to align the stuff. You can easily make a mistake here, so I'm not really fond of this stuff. But if you see that in the homework, that's what they're asking for. To do vertical multiplication means, all right, okay, multiply this one with everybody here, put in a single line, multiply this one with everybody here, put in the next line, align them properly, and then you add them. And that's the same old story. So again, this works perfectly with numbers. I'm going to show you the number example, long multiplication. So you have 237 times 35, right? Everybody knows that, right? How that works. All right, 5 times 7, 35. 3 to remember is a conversion. 35 is 3/10, right? So you got the 5 times 3, which is 15. And I just remember this 3 I had, that was 18. Now I have to remember 1. Let's carry on 1, so you have 5 times 2, and I have 11. And then you go this one. And you go now here. Why you go here? Because this is 10. It's place of 10. Alignment is in the floating point. So 10 is here. So you have 3 times 7, 21. 2 to carry on. 3 times 3, 9. 2 to carry on is 11. 1 to carry on. 3 times 2 is 6. And 1 that I'm carrying on is 7. So now I have 5. A perfect alignment. 9, 2, 8. Works fine. I hope I did it right. I'm not quite sure anymore. Let me try again. So I have 5 times 7, 35, 3 to carry on, 5 times 3, 15, 18, 1 to carry on, 5 times 2, 10, 11. Good. Back that one place, 3 times 7, 21, 2 to carry on, 3 times 3, 9, 2 to carry on, 11. So that's 1 to carry on, 2, 3 times 2, 6, 1 to carry on, 7. And yeah, I think I have it right. All right, check it out. So this is a good old story that you probably forget, I think, right? Who remembers this stuff anymore? Everybody uses calculator, including myself, which is really bad habit. Let me check. I got this right. Yeah, I did. So that makes sense with numbers because, again, the kick with the numbers, you always have this alignment. This is floating point, floating point, floating point, floating point. This is actually 71,000. 7,110. So it's floating point here and floating point here. Perfect alignment. So with polynomials, that doesn't happen. Again, you don't have a floating point there. Can you do this? Can you do that in a single line? 235 times 37? Yeah, sure. Okay, what do we do? 235 is 230 and 5. Multiply with 37, which is 200 times 37 plus 30 times 37 plus 5 times 37. Okay? Now, what do we have here? This is 30 plus 7. So you have 200 times 30 plus 200 times 7. This is 30 times 37. This is 30 plus 7. So you have 30 times 30 plus 30 times 7. And the last one is 5 times 30 plus 5 times 7. I guess you've never done anything like that before in your life because you always learn this routine along multiplication, but much less writing. 2 times 3, 6, 0, 0, 0. 1, 2, 3. 200 times 7 is 1,400. Anybody can do that. 30 times 30, 3 times 3 is 9, 2 zeros. 30 times 7, 210. 5 times 30, 150. And 35 at the end. Now you can finish this. Well, it goes slow. So you get 7,400. Then you have 1,110. And you have 185, which is these two. 8,000, 1,000, 8,000, 100, 500, 10, 10, 0, plus 185. And you're getting 8,695, which is the same thing I got moments ago. I think I did. Nope, I made a mistake somewhere. All right. So it should be 200. So where is my mistake? Let's see. Good, good, good. 37, 30 times 30, 30 times 7, 5 times 30, 5 times 7. Good. 600, 6,000, excuse me. 1,400, 900, 210, 150, 35. 7,400, 1,110. Good. I'm out of words. I don't know where the mistake is. It should be 8,295. So you have 400 too much somewhere. Oh. You'll find it. If I, well, was I trying to do that anyway? Let's see. So I have 230. Oh, I probably have a different number here. That's why. Because I don't remember what I was doing before. Let's see. 235 times 37. Yeah, this is correct. I just have a different number probably before. I was doing something else. Right? This is what you do with polynomials. Because there you don't have a floating point. But this is what you not do. You're not doing that with the Hindu Arabic numbers because you do have a floating point. Beautiful thing right here. So you can align everything and you can do that long multiplication that looks a lot better than this stuff here. Okay? But with polynomials, you're not going to have that luck. You're really going to have to apply that rule of everybody with everybody. So 3 guys times 2 guys, all 3 pair with this guy, and then all 3 pair with this guy, and you write it all as it goes, and you do every single multiplication like here, and then at the end you add them up. Okay? So again, this, what you see here, this beautiful number, 235, and now I'm going to write something else like 2035, was brought to us, Western civilization, but by Arab merchants. And they were using that in Persia. And this number here, this 0 as a concept or as a placement, as a place, when you don't have hundreds, you just put 0 here. That was invented by Indian mathematicians. They didn't use like that. They used like this, small dot. So it took Indians, Arabs, and Persians to come up with this fantastic, beautiful concept that you write numbers nowadays with. And since 12th century, 13th century, in Europe, we write like that. Okay, so for past 700 years. So this tells you about the exchange of civilizations. Now, where are the polynomials coming from? Well, they come more from 16th century. So it took a little longer to somebody figure out, hey, we can do it with variables as well. Okay, so this is my story for today. I want you to read a story about the powers, because the power story, well, let me do one more example. Power story is just the stuff about the exponential business. So when you are doing the powers of polynomials, we're going to be talking about only monomials. You're going to simply use the power rules. So you have something like this, and you're making a cube. You have power rules: factor, factor, factor. By the power rule, the exponent goes on each factor separately. That's a power rule. And again, I'm going to use containers. You don't have to if you know what's going to happen. And I'll use a power rule. Well, this is not really a power rule, it's just multiplication. 3 times 3 times 3 is 27. This is a power rule, 7 times 3. And this is a power rule, y, 2 times 3 is 6. So that's not much of a story here. Powers of monomials are just simply power rules. Okay? I want you to do the homeworks. Well, only one. This says polynomial basics. That homework is kind of lengthy, but it will give you a little more handle on polynomials. How do you, again, what the polynomials are, what is the degree of the polynomial, what is the leading coefficient of a polynomial, what is the leading term of a polynomial. We'll also teach you how to add them, which you see a couple of examples here, how to multiply them, subtract, of course, And one thing is missing, right? And that is, how do you divide them? Well, that's a little more complicated story. Now, with numbers, we are dividing numbers by using a long division. With polynomials, we also have a long division, but because of the absence of floating point again, that long division is going to be a little more complicated than with numbers. So I have to have a whole lecture on that only. So division, we'll leave it for some other class time, okay? So a bunch of the stuff in that homework on polynomial on basics of introduction to polynomials is now available to you. I want you to do that while you're fresh, so that you can still have that in your mind, all of these examples, so you can work it out while you still have that memory of it, right? Don't delay, because when you delay, it's gonna, everything you delay, you forget, and then it's always much harder to do later down the road. Okay, I'm done with this story today. So I'm gonna end up the stream, and if you have any questions about it, you can write me an email, or you can just simply go and watch this lecture over again, right? I'll see you on Wednesday.